let's start with some questions. Okay. What causes flow voids? So flow voids are caused by the spin echo. In my experience, whether it's a T2 weighted image or a T1 weighted image, if there's a spin echo, arteries are going to look black. That has been my experience. So I want to now go through why that is the case. So in order to do that, we have to understand a little bit more how MRI sequences are obtained. So I haven't talked about this, but for 2D MRI imaging, we're generally applying the 90-degree radiofrequency pulse, not to the entire volume of tissue that we're interested in imaging, but just one slice at a time. So let's say that we apply this 90-degree radiofrequency pulse just to slice number 2. And let's just consider 3 components in this slice. The internal carotid artery, which we'll abbreviate as A, the internal jugular vein, which we're going to abbreviate as V, and the spine, which we'll abbreviate as S. So those are the only 3 things that now have transverse magnetization: the internal carotid artery, the spine, and the internal jugular vein. Even though eventually we're going to image the rest of the patient's head and upper neck, at this point, all of the magnetization is in the longitudinal plane, and therefore we can't detect it. The only signal that we potentially could detect has come from slice 2. Okay, so in order to sample this signal, we need to wait a certain amount of time, the time to echo, which is on the order of milliseconds, before we sample the signal with our receiver coil. If the time to echo is long enough, the artery and the vein, the blood in the artery and the blood in the vein, will move out of the slice at the time that we're sampling the signal. So, question, is that the reason for flow voids? That's initially what I thought, but the answer is no, and this is important. We detect signal from anywhere the receiver coil is located. So if we're using a head coil, then we're going to detect signal anywhere in the head. Even though we generated signal only from slice 2 in the upper neck, we'll be able to detect that signal even if it moves, as long as it's within the domain of the head coil. And there's some coils, like body coils, that can cover almost the entire patient. So the reason that we have flow voids is not because the signal moves out of the slice where we generated it. It would have to move out of the domain of the receiver coil, which is very unlikely for that to happen. So that's not the reason for flow voids. So what is the basis for flow voids? So let's consider the following sequences. So this is a T1 weighted image because the white matter is white relative to gray matter, and these are T2 weighted images because the white matter is dark relative to the gray matter. And this is a T2 star weighted image because it's relatively grainy. The CSF is bright, so it's either T2 or T2 star. Since it's grainy, it's the T2 star. This one is crisp, so this is the T2 spin echo. So where do we see the flow voids the best? It's right here. We see the basilar artery, black, internal carotid arteries, black, nice flow voids. Here on the T2 star, I may as well fill this in. On the T2 star, we see the basilar artery is black, but the internal carotid arteries are kind of white. So that's not the best for flow voids. And the T1 gradient, that's the worst, right? The basilar artery is bright, and the internal carotid arteries are also bright. So why is this? Why is the T2 spin echo the best for looking at flow voids? Okay, so the main principle is that it's the spin echo sequence which causes the flow voids, but I'll come to why the T2 spin echo is even better in a minute. So the reason is because the arterial and fast-flowing venous blood move outside of the slice at TE/2 when we're giving the 180-degree radiofrequency pulse that generates the spin echo. So let's review. To acquire a 2D MRI pulse sequence from a particular volume of tissue, we're going to only excite one slice at a time. So let's say we excite slice 2 with the internal carotid artery, the internal jugular vein, and the spine. Shortly after that 90-degree radiofrequency pulse is given, the artery and the venous blood are going to move out of the slice. Fine. At TE/2, the 180-degree radiofrequency pulse is given to the same slice. Why do we do that? That's how we generate the spin echo. just to quickly review, if this is the blood product, if this is the water spin, this is 1.6 Tesla, this is 1.5. The 1.6 Tesla is going to precess faster than the 1.5, creating phase. That phase is going to cause signal loss, right? That's the T2 prime related signal loss. So we flip the spins 180 degrees, right? And then the faster moving spin is going to catch up with the slower one. We're correcting T2 prime at TE. So that's the point of the 180 degree radio frequency pulse. At TE over 2, it generates that spin echo to correct T2 prime. So the artery and the vein, though, they've already left the slice, so they don't see the 180 degree radio frequency pulse. Therefore, what is the time constant which is going to describe how quickly their transverse magnetization is lost? How the transverse magnetization is, or how the spins are dephasing. So that's going to be T2 star, right? T2 star describes spins that have not seen the 180 degree radio frequency pulse, right? We're losing transverse magnetization not just due to T2, spin-spin energy transfer, but also due to T2 prime. So that's where they're going to be at on the curve, very low signal. Whereas the spine, the stationary tissues, are going to lose transverse magnetization with a time constant of what? T2. Since they saw the 180 degree radio frequency pulse, they're going to get that signal boost. They're going to get that spin echo, which we just described, right? So in short, flow voids are not due to signal loss from failure to get, flow voids are not due to flow-related signal loss. You'll hear that. At least that's not how I think about it. Flow voids are actually due to the stationary tissues getting a boost from the spin echo, whereas the flowing blood does not. So the stationary tissues lose transverse magnetization with the time constant of T2, but the flowing blood loses transverse magnetization with the time constant of T2 star. That difference between T2 and T2 star, that's the reason for the flow voids. The flow voids are on the T2 star curve, whereas the stationary tissues are on the T2 curve. So why not use a T1 spin echo pulse sequence to look at flow-related hypointensity in the head? So most arteries in the brain are surrounded by CSF, which is dark on T1 weighted images. So you don't get as good contrast with a T1 spin echo image, right? Because the arteries are black and the surrounding CSF is black. That's one practical reason why it's better to look at flow voids in the brain with a T2 weighted image, because the arteries are black and the CSF that surrounds it is white. Another reason, though, is that T2 weighted images have a longer TE than T1 weighted images. Remember, in order to take advantages of those differences in the T2 properties of tissues, we need to wait a relatively long period of time relative to where signal is maximized in order to sample the signal. So the longer the TE is, the longer TE over 2 is, and therefore there's a greater chance that the flowing blood is going to not see the spin echo. Basically, the longer out we can put TE over 2, the more likely we are to have a flow void, essentially. Okay, so what contributes to flow-related hypointensity, aka flow voids? So the answer is movement outside of the image slice at TE over 2 on a spin echo pulse sequence. So again, the key associations are that flow voids are related to spin echo, okay? And it's due to the moving spins not seeing the 180 degree radio frequency pulse, which is at TE over 2. The fact that the spins move outside of the slice at TE is not the reason for flow voids. Remember, we have a receiver coil which can detect signal pretty much anywhere it goes in the head. So that's not the reason. Are these spin echo images or gradient echo images? So these are T2 weighted images. The white matter is dark relative to the gray matter. CSF is bright, relatively crisp. So these are T2 spin echo images. Another way to tell is to look at the arteries. So if the arteries are black, then we're dealing with some kind of spin echo image. So that's how I like to tell if I'm dealing with a spin echo or gradient echo image. I go to an area where I know there's an artery. If it's black, then it's a spin echo image. So these are T2 spin echo images. And what do these images suggest? So they suggest a left ICA occlusion with distal reconstitution. So I paired these T2 spin echo images with the corresponding CT angiogram. Same patient. So here we're at the level of the horizontal petrous internal carotid artery, and we see that there's nice flow-related hypointensity within the right internal carotid artery, and we lose that here. And you see that nicely on the CTA, right? So there's nice contrast filling the horizontal petrous ICA, but no contrast in the left horizontal petrous. Here we're at the level of the ascending cavernous portion of the right internal carotid artery. We see a nice black signal in the spin echo sequence. We see no hypointensity on the left. And sure enough, there's no contrast on the left. When we get up to the horizontal cavernous segment of the right internal carotid artery, which we see it's kind of tortuous, we see it here. We see nice flow-related hypointensity, and we see corresponding contrast on the CTA, but on the left side, we don't see anything. We're at the level of the pituitary. That's how we know this is the level of the cavernous ICA, by the way. Then when we get up to the top, though, check this out. Now we see flow voids, not just on the right, but also on the left. So what happened? How are we, and sure enough, on the post-contrast, on the CTA, we see contrast in the left supraclinoid ICA as well as the right supraclinoid ICA. So what happened? So this is reconstitution by the circle of Willis, most likely. I don't know if we directly see it here, but there's a hint of it here. This is probably the posterior communicating artery coming here. So it could be filled by the posterior communicating artery, theoretically, or maybe the anterior communicating artery. But the circle of Willis is basically saving the day. So this is a left internal carotid artery occlusion with distal reconstitution. Why is there dark signal? Oh, and I should mention, so why don't we see a flow void in the left internal carotid artery when it's thrombosed? Well, because it's getting that spin echo boost. So if the blood is not significantly moving, then it's going to see the spin echo, and it's going to look bright just like the rest of the stationary tissues, right? So that's the reason. The blood in the thrombosed artery is experiencing loss of transverse magnetization with a time constant of T2 if it's thrombosed. When it's flowing, it's not seeing that 180-degree radio frequency pulse at TE/2, and therefore it loses its transverse magnetization with T2 star and looks relatively black. Okay, so why is there a dark signal dorsal to the spinal cord on the images to the right, so here, but not on the left, right? So if we look dorsal to the spinal cord, we see this black signal here, and we do not see that here. So similarly, on the sagittal image, we see black signal like right here, and we don't see that black signal here, it's just white. So what is going on? So this is CSF flow, right? So which of the images have to have the spin echo? It has to be these ones, right? So again, the CSF is flowing out of the slice at TE/2. Therefore, it doesn't experience the spin echo. That's the reason that it looks relatively black. So this sequence, it's a steady state free precession sequence, which is a special type of gradient echo sequence. And that's the reason that we don't have these flow voids on this sequence. There's no spin echo, essentially. Okay, blood is not the only fluid that can demonstrate flow-related hypointensity, right? Anything that's moving can have this property on a spin echo image. And right, notice how the flow-related hypointensity is not present on the other sequences. So this is a general principle. If something is not holding up on multiple sequences, multiple planes, there's a good chance it's an artifact. But now that you understand how the spin echo causes flow voids, this can help you to be more confident at diagnosing this particular type of artifact of CSF flow or blood thrombosis.